Hi, my name is Aaron Greenberg. I'm an undergraduate researcher at the University of Pittsburgh working with Dr. Jeremy Levy's group, and I'm going to be speaking today about the effect of temperature on the decay of conductivity of lanthanum aluminate strontium titanate nanostructures. The LaO-STO heterostructure is a really interesting material. It exhibits some fascinating properties such as a high mobility two-dimensional electron gas that forms at the interface between the lanthanum aluminate and the strontium titanate, a metal insulator transition, superconductivity, magnetism, tunable spin-orbit coupling, and more. Due to all of these interesting properties, we're able to pattern devices into the two-dimensional electron gas that appears at the interface between the lanthanum aluminate and the strontium titanate. We do this through a technique known as conductive atomic force lithography, or c-AFM lithography. By applying a positive voltage to an AFM tip and dragging the positively biased AFM tip over the surface of the sample, we're able to transition the interface from its base insulating state to a conducting state. By applying a negative voltage to the AFM tip and dragging the negatively biased tip over an area that's already been written, we're able to erase the nanowires, cutting any conductance that we may have patterned into the interface. This writing and erasure process does not degrade or damage the sample in any way, which leads to very high reusability of samples and ability to create many different devices in one sample. Now, we have to understand a little bit more about how the c-AFM lithography works, and that's through something known as the water cycle mechanism, where water in the air adsorbs onto the LaO surface where it dissociates into H+ and OH- ions. The positively biased AFM tip removes those hydroxyl groups, leaving just the H+ ions on the surface and producing the conducting interface. A negatively biased AFM tip will remove those excess protons from the surface, which restores the insulating state. However, we find that over time, due to excess ions in the air, we see that slowly the sample surface becomes deionized, and we are able to slow this decay of any device that we write by placing the sample into vacuum or dry gases. And we know that by placing a sample into vacuum and then cooling it down to very low temperatures, say around 80 Kelvin, we're able to significantly slow this decay, or to the point of even stopping it. It's important to be able to slow this decay down as much as possible because we are only able to write nanostructures on a scale of about 10 nanometers to 1 micron per second. So as we want to design large and intricate devices, slowing of decay allows us to create better and larger devices. So I set out to test exactly how temperature will impact the decay of devices created in LaO-STO. And to do so, we have designed two devices to measure this. First, we use a simple 4-terminal measurement, and then we've also designed a device which uses both 1D channel and a 2D channel. However, what we find is that there's no significant difference in the decay dynamics of the two-dimensional structure compared to the one-dimensional nanowire, so we will focus exclusively on the one-dimensional nanowire for this talk. In order to understand how temperature affects these devices, we first write a device in the AFM and then transfer the sample to the cryostat. We will vary the temperature every so often then, all the time while monitoring the conductance of the sample. For example, the first test that we did was looking at what happens if we decrease the temperature while holding the sample in air. For this, we used time intervals of approximately an hour, so we started at 300 Kelvin and then held the temperature fixed for approximately an hour, after which time we decreased the temperature by 5 Kelvin, allowed the sample to reach equilibrium, and then again rest for another hour. We continued this the whole way down to 275 Kelvin. In order to analyze this data and understand it, the next thing we did was we took a linear fit of each of these decay periods to find a rough slope of decay, or a linear rate of decay dg/dt. By plotting the natural log of dg/dt against inverse of temperature, we get a graph that obeys the Arrhenius equation, and we're able to then use that in order to find an activation energy of the decay of conductance of these nanowires. we find an activation energy of 0.8 eV for this test, and I would like to compare this briefly to theoretical work done by Chang Sen's group at the University of West Virginia in 2016, where they predict that the proton hopping energy of LaOSTO should be about 0.7 eV. So we're seeing some minor disagreement here. The next test we looked at was decreasing temperature in vacuum. This was the first test where we switched to both the 1- and 2-dimensional device. However, I've highlighted here that we're only using the 1-dimensional device for this data. We increased the time interval here to approximately an hour and a half, and what we find is that, I need to change that, okay. What we find here is that the activation energy when we store the sample in vacuum drops to 0.66 eV, about a 20% change in the activation energy. The next thing we wanted to consider was what happens if we increase the temperature. In this case, we wrote a sample at 300 Kelvin, and then we placed it in the cryostat and dropped the temperature down to 275 Kelvin. We then proceeded to perform the test the same way, increasing in 5 Kelvin intervals instead of decreasing. We believe that due to this sharp drop in temperature at the beginning, we get this outlier point here at 275 Kelvin in the data. So if we include this one point here in our activation energy, we see a activation energy calculated to be 0.39 eV. However, if we exclude that point and look only at these other 5 points, we see an activation energy of 0.75 eV, which is much closer to what we've seen in the decreasing temperature tests. Lastly, we consider what happens if we decrease the temperature in vacuum. And in this case, we use time intervals of approximately 4 hours, because we noticed that for the increasing temperature in air test, the decay was very slow, so we wanted to make sure that we had a long enough time interval to get a good picture of what was going on. In this case, again, we see this slight outlier point here at 275 Kelvin, and including it, we see an activation energy of 0.41 eV, and excluding it, we see an activation energy of 0.51 eV. So placing all 4 graphs next to one another, you can clearly see that as we increase the temperature, the rate of decay will increase in all of 4 tests. And likewise, when we decrease the temperature, we're able to slow the decay of these nanostructures that we create. When we look at the activation energies, we see that for tests done in air, we see activation energies on the scale of approximately 0.75, 0.8 eV, whereas in vacuum we see significantly lessened activation energies. So we'd like to mention that because of this, we're able to cool a sample to dramatically increase the device's lifespan, even through very modest cooling. But we are able to derive an estimate for the average lifespan of a device by taking the average conductance over a temperature interval and dividing by the rate of change of the conductance during that interval. And what we see is that using this estimate, we see that a device that has a lifespan of about 1 day at 300 Kelvin can have its lifespan extended the whole way up to almost 25 days at 275 Kelvin. So a very modest cooling can lead to a very significant increase in lifespan, which allows us to have new opportunities for collaboration with groups that may not necessarily have the ability to write their own devices, but instead will have the ability to perform tests that we cannot, where a group with writing capabilities can write a device, cool the sample down, place it in vacuum, and then ship it off to a collaborator group where the device will arrive in very good condition. So in conclusion, we've shown that the cooling of samples is able to slow the decay rate very significantly, and that the effects of storing a sample in vacuum compound with the effects of cooling it. So with that, I'd like to thank you all for your time, and I'd like to heartily thank my group members and ask if there are any questions. So again, just shy of 10 minutes, that puts me at about 9:45. I know I need to relabel this the annotations on a couple of these graphs, but all of this data is shifted over to be 4-terminal now. So hopefully we're getting pretty close. Let me know what you think. Thanks.